Let's take a look at Part 2, Thermal Properties of Materials, R value of a multi-layer component. This section covers pages 117 through 128 of your text. In a multi-layer building assembly, where the layers are stacked along the direction of heat flow, the combination of layers is referred to as series combination, because the heat must pass through layer 1 to get to layer 2, through layer 2 to get to layer 3, and so on. In such a layered sandwich, the amount of heat passing through each layer is the same. Based on this fact, it can be shown that the total R value of the assembly is the sum of the R values of individual layers, R1, R2, R3, and R4. So, if we were to calculate the total R value of this assembly, we would first have to look at the type of materials in each layer, and then we would go back and find the P value of each. And so for the first layer, we have a 4-inch thick brick wall. So the actual thickness of that wall is 3 5/8 inch thick. So we take 3.625 and we multiply that by the P value of brick, which is 0.2. We end up with an R value of 0.0725 for the 4-inch brick wall. The next layer in the assembly is 2-inch thick XPS board insulation. So the thickness, which is 2, times 5, which is the P value, that's for each inch, that equals a total R value of 10. 8-inch thick brick wall, we would have 8-inch, the actual thickness of the brick or the block is 7.625, and the P value of brick is 0.2, and so the total R value of 8-inch brick wall is 1.525. We then would simply add up each layer in the assembly. So 0.725 plus 10 plus 1.525 is equal to 12.25. Since R values are recorded in increments of 1, we're going to round this one down to R12 for a total R value of that assembly. In addition to the layers of solid materials comprising an assembly, there are 2 invisible layers that contribute to its R value. These layers are thin films of air of nearly zero velocity that cling to the inside and outside surfaces of an assembly. Because each air film has certain thicknesses, it increases the total R value of the assembly. So the R value of the inside air film is approximately 0.7, and the R value of the outside air film is approximately R2. So when we add these two together, we will round it up to R1 for both layers. So far we've discussed conductive heat transfer, the dominant mode in most building assemblies. The other 2 modes, convection and radiation, occur only in air spaces that exist in walls, roof ceiling assemblies, floor assemblies, and insulating glass units. Theoretically, the concept of R value is applicable only to solid components in which conduction is the only mode of heat transfer. However, the concept is extended to airspace also, and an airspace is assigned an R value just like the solid component, although the primary modes of heat transfer through an airspace are convection and radiation. Radiation heat transfer through an airspace is reduced if one surface of the airspace is lined with bright metal, such as aluminum foil. Thus, the R value of a lined airspace is greater than that of an unlined airspace. Radiation emitted by 2 objects that are the same temperature. The objects are identical except that one of them is lined or wrapped with aluminum foil. Think in terms of a baked potato. The unlined object emits more radiation or heat than the one lined with aluminum foil. Regarding the location of low emissivity material in an airspace, if we take a look at figures 5.14 and 5.15 in your text, the main difference between these two is the location actually of the emissive layer. So the foil in the first one, if the heat is coming from the left-hand side of this, it's going to reflect back into the airspace once it gets to layer 2. In the right-hand side, if our aluminum foil is on the warm layer, which is number 1, less of that heat or energy is going to get into the airspace. And therefore, the location of the aluminum foil does have an impact on the R value of the airspace, but not the other solid materials. So let's determine the R value of a typical wood frame wall with brick veneer and a 2-inch airspace. So if we start out on the inside surface, which is going to be up here, this is your inside surface, this is your outside surface. The inside surface resistance, that film on the inside surface of the wall, is going to be 0.7. Half-inch thick gypboard, and we'd have to go back to the p-value table, which is in the previous section. So ½ inch is the thickness. The R value of that, or the p-value, is 0.6. So our R value for a ½ inch thick gypboard is 0.30. 3.5 inch thick fiberglass insulation, and that's going to be in the stud cavity. So we're actually figuring the R value of the insulation and not the studs in this case. So I've got 3.5 inches thick times 3.5 inch, or 3.5 p value, and that gives me a total R value of 12.25. On the outside of that, we have a ½ inch thick plywood. P value on that is 0.9, so we end up with an R of 0.45. And our 2-inch airspace, which is this gap right here, we have an R value for the airspace, which is 1. And then I have 4-inch nominal thick brick wall. So our actual thickness of that brick is going to be 3 5/8. So we use 3.625. Our P value is 0.2. And we get a total R value on the brick veneer of 0.73. Our outside air film is at 0.2. And so if we take and add all of these R values up, we'll end up with 15.6. So since we're at 15.6, we have to round this up to 16. So our R value of this assembly is going to be R16. U value and U factor refer to essentially the same concept. But in our text, we use the term U value for an individual assembly, such as an opaque part of a wall, a window, a door, roof, skylight, and so on, where an assembly consists of multi-layer parts arranged side by side, horizontally or vertically, as shown in figures in your text. The overall U value of such an assembly has been termed as a U factor, designated by symbol U. U value is the inverse of R value. So if we take the R value of our multi-component assembly and add them up, we'd basically take those and we would divide 1 by the sum of those numbers. That is the U value. It's the inverse of R. Again, this concept becomes useful when we have something as complex as like a window or a door. If you look at a window, you might have aluminum cladding, aluminum cladded wood window, you've got an insulated pane of glass, you have gasketing, and different types of materials. I've just mentioned 4 different types of materials. Each one of them has its own separate capacity to resist energy flow through that material. So U value comes in handy when we have to account for several different R values in the same item. Heat flowing through an assembly with several parts arranged side by side divides itself into parallel paths. Heat flow through each path is not the same in contrast with the assembly in series combination. Again, think in terms of doors and windows that penetrate a typical wall assembly, like the brick veneer wood stud wall that we looked at earlier. Each has a different U value and certainly different R values. So as we begin to look at an assembly or a group of assemblies as a whole, we have to use U value to make the calculation of that assembly's efficiency. So how would we go about calculating the U value of a wall, for example? I'd have to take each individual piece. So it looks like we have a door and 2 windows, and each one of those pieces has its own U value associated with it. So we would take and we would multiply the area times that U value, and we would divide that by the total area of the assembly, and that would give us the overall U value of that particular assembly. So if our overall U value of this wall assembly is 0.24, if I wanted to find, or if I wanted to know the equivalent R value, I would simply take 1 and divide it by the U value. So in this case, the overall R value of this wall is 4.2, and that's an average based on the areas of each individual component and their U values. This is the end of Chapter 5, Part 2. Now it's time to complete the quiz on Chapter 5, Part 2.